In this section, we're going to look at the problem of deciding which method to use to test a series for convergence or divergence. You should start, of course, with a firm knowledge of each test and the ability to recall quickly the details of the test and when it can be applied. So let's have a look at what we have in our toolbox. First of all, we had the divergence test, which says if the limit of the nth term of the series as n goes to infinity doesn't exist, or if it's non-zero, then we can conclude immediately that the series diverges. If that limit is zero, then no conclusion can be made with the divergence test. Geometric series, if you recognize them, are pretty easy to deal with. They are of the form the sum n equals 1 to infinity of a times r to the n minus 1, and they converge if the absolute value of r is less than 1, and they diverge if the absolute value of r is greater than or equal to 1. And we can do more than conclude convergence here if the absolute value of r is less than 1. In fact, we can write down the sum. It's a over 1 minus r. And remember, in deciding what the a and the r are, if you expand the series, a is the first term and r is the second term divided by the first. And of course, these series may have positive or negative terms, and we use the absolute value of r to decide on convergence or divergence. The harmonic series is something you should always keep in the back of your mind. It's divergent, and that series is the sum from 1 to infinity of 1 over n. Telescoping series are pretty easy to deal with. Here the terms are of the form f of n minus f of n plus 1 for some function of n. And the reason that you can deal with them easily is the partial sums are easy to calculate because of the large amount of cancellation, and then you can take the limit as n goes to infinity of the partial sums to actually find the sum or show that it diverges. The integral test is something we used as a means to an end. We used a particular function, 1 over x to the p, to conclude which p series converge or diverge. So a p series is of the form the sum from 1 to infinity of 1 over n to the p, and you should know that that converges for p bigger than 1 and diverges if p is less than or equal to 1. The comparison test applies only to series with positive terms, but of course it can be applied to the sum of the absolute values of the terms of a series to conclude absolute convergence. If we have two series, the sum of an and the sum of bn, if an is less than or equal to bn for all n, and the sum of bn is convergent, then we can conclude that the sum of an is also convergent. If an is greater than or equal to bn for all n, if the sum of bn is divergent, then we can conclude that the sum of an is also divergent. The limit comparison test is easier to use and can often be used in place of the ordinary comparison test with a few exceptions. And this says that if I have two series, the sum of an and the sum of bn with positive terms, and if the limit as n goes to infinity of an over bn is some constant c, where c is greater than 0, then either both series converge or both diverge. The alternating series test, of course, applies to an alternating series. If I have the terms of the series are of the form minus 1 to the n minus 1 times bn, where bn is positive, or minus 1 to the n times bn, where bn is positive, then if the limit as n goes to infinity of the positive part is 0, and bn plus 1 is less than or equal to bn for all n, then I can conclude that the series converges. And in fact, I can conclude this if bn plus 1 is less than or equal to bn for all n bigger than or equal to some fixed number. We say a series is absolutely convergent if the sum of the absolute values converges, and it's conditionally convergent if the series itself converges but the sum of the absolute values does not converge. And of course, if a series is absolutely convergent, then it's actually convergent. So if the sum of the absolute values converges, then we can conclude that the sum of the series itself converges. The ratio test can be applied to series with either positive or negative terms. And if I take the limit as n goes to infinity of the absolute value of an plus 1 over an, and I find it's equal to L, where L is less than 1, then the series converges absolutely. If that limit is L, where L is greater than 1, then I can conclude that the series diverges, even if that limit is infinity. But if the limit equals 1, then the ratio test is inconclusive, and I have to find some other way to decide whether the series converges or diverges. And the root test is very similar. If you take the limit as n goes to infinity of the nth root of the absolute value of an, if that limit is less than 1, the series converges absolutely. If it's greater than 1 or infinity, the series diverges. And if it's equal to 1, then the root test is inconclusive. And we have to use some other test to try to determine convergence or divergence. Well, the big problem is faced with a series. How do we decide which test to use? It's good to have worked through several examples from each of the sections on each series to get a feel for where the tests are best applied. So if we have a series and we want to test it for convergence or divergence, a good place to start is calculate the limit as n goes to infinity of the nth term of the series. If this is not equal to 0, then we can immediately conclude that the series diverges. If it's equal to 0, then we have some work to do. We have no conclusion from the divergence test. You might recognize it as a geometric series or a p-series or a telescoping series, in which case you can almost immediately tell whether it converges or diverges. It might be the sum or the difference of two well-known converging series, in which case you can break it into the sum or difference of these two series and perhaps conclude convergence or divergence from that. The integral test, again, was something we just used as a means to an end to determine whether p-series converged or diverged, but it can be applied more widely. If a series is roughly of the form the sum of 1 over n to the p, we might recognize this and we can compare it to that p-series using a limit comparison test, or we might recognize it as roughly being a geometric series, in which case we should use the limit comparison test to compare to the appropriate geometric series. And when using the comparison test, we can either use the direct comparison test or the limit comparison test. Both of these only apply to series with positive terms, but if a series has negative terms, then if we can prove that the sum of the absolute values converges, then the series converges. The comparison test is especially useful if the terms an are rational functions of n. And then, of course, the trick is to divide the highest power of n in the denominator by the highest power of n in the numerator to figure out which p-series we should compare to, and then, of course, apply the limit comparison test. If series have negative terms, of course, you should keep in mind that absolute convergence will imply convergence. So if you forget about the minus ones or the negative parts, and you can conclude convergence using the limit comparison test, then you've got convergence. You may be able to use the alternating series test, and in order to conclude convergence from that, you just need that the terms are decreasing in absolute value, and the limit as n goes to infinity of the absolute value of an is 0. If you have factorials or powers of a constant, then the ratio test is probably going to work, and it's a very good test to start with. It will not work for series that are similar to p-series, where the terms of the series are rational functions in n. And if the terms of the series are nth powers, then the nth root test will probably work. If the ratio test is inconclusive, then the nth root test will also be inconclusive and vice versa. So if one doesn't work, then there's no point in wasting time trying the other. You should try some other tests, such as the limit comparison test or the alternating series test.